So we had a little bit of trouble with the display, but finally we got started. And thank you for making this so early in the morning and on a rainy day, which is perfect for people from Seattle, but no. Yeah. So today I'm going to talk about SONiC, software for open networking in the cloud. And this is really work that beyond my team or beyond Microsoft. This is actually a community work that happened between many, many different companies in the SI and the SONiC community. So really I'm speaking about the work for the broader community instead of a single group or anywhere, right? So when I see the SONiC and the SI community, what do I mean by the community? At the bottom, you see a whole bunch of companies that build switch ASICs. You see companies like Barefoot, Broadcom, Mellanox. The Cisco also have their own ASIC, Marvell, Innovium, Centec, Cavium. Right? So quite a few different companies that build switch ASIC. And they also provide this layer, what we call SI, Switch Abstraction Interface. That is a common API layer across all the ASIC vendors, kind of the standard API layer that everybody gets to leverage. Then in the upper layer, you see quite a few switch box integrators. Those boxes basically put the switch ASIC into a box and build a form factor, right? 1RU, 2RU, whatever that is, and make it available. Right, so those SONiC sits on top of this box as a software, right? And so quite a few different companies are contributing software stack in this ecosystem, right? Running on the boxes. You see certainly Microsoft, and you see the contributions from Docker, Canonical, Mellanox, Alibaba, Tencent, Metaswitch, all kind of different companies in the ecosystem, right? This is a snapshot that we had in the March 2018 OCP. It takes quite a bit of work to get a legal permission to put another company's logo on it, so we didn't really bother to update it, didn't have enough time for that. So hopefully we'll have another round of update with a lot of new community contributors in the next year's OCP Summit. And what is SI and SONiC? Just to kind of refresher, SI is the initial OCP contribution in December 2014, so it's been quite a few years. It provides a common API and behavior model across multiple ASICs so that you can think of the hardware for one time and reuse your application level code across different hardware instead of every single hardware ASIC comes into birth, you need to kind of refit all your software development. So that's kind of the enablement for hardware and the software disaggregation. And also, certainly, it helps us to achieve the independent evolution of hardware and software. The reality is that the hardware and the software are both evolving at a very quick speed, but they may or may not be at the same cadence. So the independent evolution of them are very important to get the speed up. It's certainly an open community that everybody contributes their ideas and try to drive the standard. SONiC is a follow-up contribution happened a little bit like 18 months later. It provides a layer 2 and layer 3 functionalities ready for cloud deployment. It emphasizes on a loosely coupled modular design and separating the states and logic in the system design so that we can develop the software quickly. And it's built on top of Debian Linux. So why is Microsoft interested in doing this? I think the broader context, right, is that Microsoft is building a network infrastructure that is a $15 billion bet in the infrastructure globally, right? And what you can see, and also from Mark's talk yesterday, you see Microsoft have 54 regions across all the places in the world, and with thousands and thousands of miles of fiber optics connecting them together. Right, all the DCs are there, right? So, and that's why we put a lot of emphasis on the software infrastructure, on the networking infrastructure. And in that context, right, when you get into a data center level, you see that we have the cross network, typically across all the hyperscalers. That at the tier 0 you have a rack level switch. And the tier 1 row level, and tier 2 is what we call the data center level spine. And at tier 3 is the regional spine, right? In that level, where is SONiC deployed? SONiC is deployed at the tier 0 and the tier 1 level in our data center broadly, right? So what is the goal of SONiC? At the bottom, you see that we are trying to move towards an open and modular software. By that, we're trying to enable the choices of vendors and the platforms in our data center. At our scale, we have to allow the competition in the hardware and the software space. With that, we are trying to make the technology evolution a lot faster than it was in the past. Eventually, what we're trying to achieve is to be able to significantly reduce operational burden that we have to put into a network. Here's a kind of detailed drill down of SONiC. So in the following part, I'm going to talk about SI a little bit, and then move on to the switch state service, which is a modular design of the SONiC. For people who have attended our talk in the past in OCP at San Jose, you probably heard about that portion already, but I'm going to provide a quick recapture of that. And the containerization of SONiC. At the end of it, I'm going to talk about the operational scenario of SONiC. So for SI, it's like I mentioned, right? So there's many ASIC, and all the ASIC SDK speaks a very different data model and a very different programming language as well, programming paradigm. So it's really that in the past, if you think about when you need to move your switch NOS stack from one ASIC vendor to another, it's typically at least 1 year, but longer, 1 to 2 year kind of development cycle for you to move to a different switching ASIC. So that is often the killer when you need to kind of look into other ASIC technologies. So basically, SI provides a translation layer so that you're talking to the same, you're talking in the same language, but to a different set of hardware there. So it allows you to build a simple and consistent, stable network application stack, even though you are moving across a hardware stack. And the actual manifest of SI is actually a CRUD operation of over an extensible set of entity attribute value kind of data model. So it's in a sense, it's a kind of table-based API that doesn't force you into certain programming language or force you into a certain paradigm. So it also provides a reference data plane behavior model that supports various devices. This reference data plane behavior model actually took all the architects from quite a few different ASIC companies to sit in the same room together and argue with each other and debate with each other so that to reach the consensus. So it took this reference data model is actually where the gist of SI is, and it takes quite a bit of people, many works there. Since its initial announcement, there's a lot of feature and partner growth. If you look at the GitHub repo, you can find all the SI specs, both the header files, the initial the design specs, and you can probably find a lot of debates there also. So it's very interesting to understand how people actually think about the network reference model. And so how is the function calls and the pipeline behave in SONiC, right? So basically, you can look. If you look at the bottom, you see a reference pipeline of hardware. You have a port, you have the RIF and the route, desktop, neighbor, those kind of things, then go to the egress, right? And then it maps to a set of SI API's calls to achieve the certain functions. And so basically, what when people need to use SI to program in the hardware, they basically use you just need to make sure the order is correct to execute the SI function calls, and then you can build the reference pipeline with the right packet action flow. So it's that straightforward. So I'm talking about the switch state service a little bit. If this is the overall SONiC high-level architectural diagram, right? So you see the switch hardware is essentially a switching ASIC, transceivers, fan, power, LED. That's an oversimplified version of it, right? And if you look at the Linux, it actually manages the hardware very well, right? For fan, power, LED, and in many situations, even the transceivers are managed pretty well by Linux, right? So we are basically saying that we took Debian and we work with platform vendors to integrate those into the sysfs place, right? So that we leverage the existing Linux ecosystem instead of inventing another one. Then the ASIC, a lot of parts of the ASIC where you expose the ports needs to be exposed as a network device, NetDev device. Right? And then the other parts of the control of the ASIC needs to be exposed via ASIC SDK towards SI. And the switch state service sits on top of it to interface all the network applications. So here's a deep dive into switch state service, right? In the middle, the essence of a switch state service is just a database. It's a Redis-based database. And it persists all the SI objects that you think of SI as object model, so you need a place to store the data, object data. And then for northbound, in order to talk to the application is going to create an application database, and then the orchestration agent is responsible for translating between the applications and the SI objects, and to try to resolve the cross dependency and the potential conflicts among the objects, right? So if you are a person who has built layer 2, layer 3 stack, you probably know that when you're trying to resolve a layer 3 routing entry, the layer 3 routing entry needs to resort to a layer 2 entry instead, and the layer 2 entry needs to be connected to interface, right? So there's a chain of dependency that need to be resolved, right? So, and the syncd lower there is basically just translating between the not translating, but the read and write between the SciDB and the actual SI to the hardware, right? So it's just a synchronization between the software and the hardware layer. So each components here, the goal is very kind of distinctive and somewhat independent. They all work around the database, but they are not coupled to each other, right? So the goal there is that we can evolve each one of the components very independently. So here's a deeper look at how SI objects are stored in the SI database, right? So application DB is application oriented, right? So it's for routing, it's a routing database. For layer 2 switching, there's a layer 2 switching database. But for the SciDB, SciDB is SI oriented, and it's queryable and machine passable. And it's basically a snapshot of the current SI state that is what is mapped to the hardware, right? So, and you can see that APIs are pretty much just simple CRUD APIs. Yeah. So I talk about the application here, right? The typical application is routing. If you look at BGP, right? We take currently SONiC takes Quagga's BGP routing stack, and if you look at the top, there's a BGPD, which essentially is a speaking Zebra, and we add a FPM syncd layer that takes the Zebra routing entry and writes the application database. The application database writes towards through the orchestration agent and through the SciRedis call to get into SciDB and writes to the hardware, right? So, and you see on the left side that basically there's a host interface exposed by Linux as a NetDev to the socket, so that you can build a BGP daemon there. And here's another one that is the lag. I'm showing you both so that you can see that the programming paradigm of adding a new application is almost exactly the same. It's pretty repeatable, but the components are very independent of each other, right? So in this case, instead of using Quagga, we put a TeamD there, which speaks the lag protocol, right? And for lag, it's a little bit more complicated in the sense that the TeamD's NetDev and the host interface are a little bit different because you need to create the lag interface, right, and manage the lag interface. So the driver there is a little bit complicated, but it's still exposed to the Linux socket. So instead of building a different socket interface, we stick to the standard Linux socket, right? But everything else is the same. The team syncd sync the data from TeamD to the application DB, and then everything flows in the same way. So following this kind of development paradigm, we were able to kind of add quite a bit of features to SONiC over the time. On the left-hand side, you see the release of 2018.03. 03 means March. That's a March release. All the feature list, and you see the common ones like BGP, lag, ECMP, SMP, and at the lower, you see some of the applications that is more driven by the cloud use scenario or our operational experience. For example, critical resource monitor. That is the one that monitor all the ASIC hardware resource. And for example, routing entry, for example, echo entry, anything that is limited, right? The reality of the hardware is that every single hardware, you have a limited set of resource. And as the cloud scale grows, it's pretty easy for you to kind of hit the resource boundary and the hardware could no longer deal with it, right? And we put in Everflow, that is our troubleshooting system, that basically is the one that allows us to do packet capture anywhere in the network. Right. There's a lot of emphasis on RDMA because Microsoft, we operate our network with a lot of emphasis, heavy use of RDMA. And from the operational experience, we add this PFC watchdog, which is if you operate RDMA for a while, you will know that it is pretty easy for you to get this thing called a PFC storm, meaning that some hardware 140 and decide to send a lot of pulse frame in the network. And that has the potential of killing your network, right? So you have to be able to detect the source of PFC storm very quickly and react to it, right? And recently, we have been working with the community to add in the 2018-07 and the upcoming October release to add features like streaming telemetry and the data plane telemetry, which is work with Barefoot, and warm reboot. Open optical monitoring. We also are moving towards Debian 9 distribution. We're currently on the previous one, Debian 8. We're moving towards Debian 9, kernel 4.9, and adding stuff like VXLAN, L3 VRF. In the upcoming, going forward, we have a plan to switch to FR as the main routing engine, full VRF support, L3, MLAG, SFlow, BGP EVPN, and we're also adding specs inside about net support. I'm happy to walk through the details of the other features, So among the features, right? We are also moving towards the container-based development model, right? So this SONiC is completely containerized already. And so basically, every application in the system is a container for us, right? For example, you will see TeamD, LDP, BGP, every one of it is a container. And this gives us a lot of benefits. The container is pretty good at providing clean isolation, and it's pretty easy for deployments, and it gives you a transactional kind of syntax. And you can run it universally, write once and deploy it everywhere, right? So for us, it translates pretty easily to something that is very serviceable, extensible, and give us some development agility and some cross-platform gains there. I'll get into more details here. For example, right, if you take a deeper look at the routing stack, right, there's many choices of routing stack. And frankly, the routing stack is not something that one size fits all, right? You have different contexts, and you probably will prefer to use different routing stack, right? So, and those stacks are probably developed in different environments. For example, sometimes one company might be developing the routing stack on Red Hat, but SONiC is based on Debian. Maybe you are developing on BSD, and the base OS is different, right? And the build environment is also different. And the situation that the source code may or may not be available, right? So example here is that the Arista BGP stack, the source code is actually not available to us, right? But as long as it's a container, and we can actually pick the container and on the individual container component basis, and we can install the container to interact according to the programming model without forcing the availability of source code, without forcing the commonality of the development environment, without forcing the base OS image. I'll get to the operational scenarios a little bit. So the first operational scenario I'm going to talk about is towards faster evolution. Right? I mentioned earlier that the whole goal of doing SONiC is to allow us to evolve the technology we have very quickly. And by evolving the software stack, you are inevitably need to kind of upgrade the OS, upgrade certain components of it, right? So I'm going to talk about 3 upgrade mechanisms in SONiC, which can be used at a different context. The first one is a fast reboot, which is already available in SONiC, right? So fast reboot, if you look at the sequence of events, right? At some point, your control plane decide I need to do a fast reboot upgrade. So basically, this is a control plane, and your control plane is going to be down for a while. But the key thing here is that when the control plane is going down, we're not turning off the ASIC, right? So when SONiC comes back and restarts, the CPU comes back and reboot it. And that's where, after that, we actually reinitiate the ASIC, right? So the data plane downtime is less than 30 seconds, and fast reboot can finish it, right? So depending on the platform, I think that we have been able to reach this requirement in pretty much all hardware platforms. And this is a situation that you can get a clean reinitialization of the ASIC. Right? So you are able to fix some of the residual bugs in the ASIC or the SDK level. Right? And this is a warm reboot. Warm reboot is a lot more gentler than fast reboot. So basically, the control plane goes down the moment warm reboot starts, right? But the data plane and the routing stack remain intact. So after SONiC comes back, right, the ASIC initiates instead of a clean reinitialization, it goes into a warm reinitialization mode. So the data plane downtime disruption is within a second typically. Right? Sometimes it's 0. And but it requires you to have a state reconciliation at the side level with the state-driven API to make sure that you're coming back with exactly the same old state. And then warm reboot finishes, right? And so you can get back to your normal operational paradigm. In the middle of it, there's the potential of downtime is actually due to the routing update that happened when your control plane is actually disappeared for a little bit of time, right? During the interval that your control plane went down, if there's new routing updates, you have to reconcile that. So that's where the potential of downtime happens. Yeah. So notice here that warm reboot is faster. The downtime is faster than the fast reboot, but the SDK doesn't get to fully reinitialize, right? So typically, you get to upgrade the SDK and the side level across minor versions. But when you are going across major version updates on the SDK level, when all the schema has been changed, it gets tougher, right? And then the even gentler version is what we call the hitless upgrade through Docker, right? So basically, the goal here is to actually reach 0 downtime. But another thought is that there's a lot of application when you try to update it. You're not really needing the data plane intervention at all. For example, when you try to upgrade your SNP container, why do you need to touch the ASIC at all? You probably don't, right? When you try to add a streaming telemetry capability, you may not need to touch your switching ASIC at all. So that's a goal here, right? So and probably that's majority of the cases where you're trying to provide a security patch to your Linux. You try to add a security patch to your other components, right? So it's and you are trying to add a new container. For example, you're trying to add a debug container or troubleshooting container on top of the SONiC OS. In that kind of situation, we're trying to not touch the switch ASIC at all, and just and the scenario here, right, is that the SONiC is already with a container, and we use Swarm to kind of roll out the container in the system, right? So I don't think the video is going to play here, but yeah. So there's a Docker registry up there, and if you're interested, I think this is actually a very normal Docker Docker container rollout scenario. That the thing here is that our demo is about the Leaf is originally speaking Quagga, and we're upgrading it to a Go BGP stack, and we are putting the graceful BGP to the both end so that your neighbor is not going to tear down the routes while the container in the middle go for upgrade. Right. So I talk about the first operational scenario, which is a fast evolution with all the upgrade mechanism. The second operational scenario is actually about emulation. That means we're not doing the real thing in the network, right? And the thought is that if you look at all the astronauts, right, they don't really fly to the sky just for the first time and they try it out, right? They're going to die, right? And right, so what they do is that they actually have a gazillion of emulation mechanism, and it's very, very high fidelity, right? And think of if you are a network operator, if you get to try your operational scenario, knows what's going to happen, and figure out all the potential mistakes you're going to make before you actually go for the real fly, then you have a much higher chance of success, right? So that's a basic premise of our thoughts there. And with that, right, so we're going to release this thing called the Open Network Emulator with SONiC. And the idea is simple. You have in your actual production network, you have many, many nodes that are connected together, right? You run certain configuration with certain software and on the real hardware, right? And the only thing we're trying to do is that we want high fidelity, but we cannot afford to kind of have a replica of our network, right? So let's use the cloud, the Azure cloud, to emulate the network, right? We use a SONiC virtual switch that's actually available on the GitHub, and put under the hardware, put under this side is actually all running on Azure, right? And the virtual hardware is running SONiC, and we put the actual configuration that we're running in production, and we just deploy it, right? And we can reach scales of thousands of switches easily in Azure, and run through our operations. For example, in one of our most complicated scenarios, what we call regional network migration, right? We are migrating the whole live network with terabits of traffic from one side to the other side, right? From the old device to the new device. And there's a lot of routing design that needs to happen, right? So we basically use this as our practice ground and emulate this and let it happen, right? So this is how it actually happens, right? The Azure engineers, we have our change manager, we have people that runs a wide area network, we have people that are responsible for the optical link, and we have people that are looking at the routing very carefully, right? And we put the actual network into the one emulator and just run it, and operates exactly the same step, same mop, and look at the routing paradigm and see what happens. If everything goes well, let it go. Right? And if anything goes wrong, it doesn't do any harm. Right? We know what's going on there. Yeah. So that's the end of my talk. And there's an open invitation for everybody to join the community. Right? Certainly welcome new ideas, new requirements, new scenarios that you have in your mind to leverage the open software. And if you have new features, applications, tools you want to contribute, we're more than happy to hear from you, right? And please download and test, and better yet, deploy in your network and see how it goes, right? And we have a bi-weekly SONiC and SI meeting. You're welcome to join the call and just join the community and talk to us and drive things together with us, right? And there's some point to start from. And, thank you very much for your time.
So if you're new to SONiC and SI, that was like drinking from a fire hose. Lots of information. We're going to open it up for questions now. And I know you can talk directly to the speaker, but because we are recording it, if you could just raise your hand, I'll bring you the mic, and then everyone who's watching the recording can hear you also. So we'll open it for questions now.
Any questions? Yeah.
Hi. You're saying that you currently have SONiC deployed on the top of rack. And
We have both top of rack and the T1.
Yeah.
T0 and T1.
Any plans to extend that to other use cases, the tier 2, tier 3 switches or beyond?
Yes, there is plan and just doing the works. So it's a little bit too early to kind of talk about the concrete plan. But yeah, we're looking into that.
Okay.
Yeah, and the challenge. So there are some companies runs a tier 2 and tier 3 with a single ASIC device, pizza box. In that kind of scenario, that would be relatively easier. At our scale, we typically run the tier 2, tier 3 with big chassis, right? So big chassis brings its other complexities, right? So in terms of hardware management, mostly. So that's one thing there. In the OCP in March, we actually talked about two potential programming paradigms. One is the demo we had with Arista on SONiC on 7512 and 7516. So basically, that in that model, the whole chassis is exposed as a single SI instance, right? So SONiC sits on top of it and manages the whole chassis through SI instead of each individual ASIC, right? So which is kind of probably the most straightforward way to think through, because we do not care about the ASIC detail, right? How the circuit gets laid out. So we don't care about how the chassis gets laid out. That's one paradigm. In the other paradigm, in one of the VXLAN implementation that we talk about, is actually that the switch state service database get branched into two portions, two ASIC, right? Two database SiDB. One SiDB for one ASIC, one SiDB for one ASIC, right? So the application needs to be modified a little bit to know that which part of the routing entry needs to go to the left SiDB, which part of the routing entry needs to go to the right ASIC, right? So that needs to be modified. But we got a kind of working prototype as well. The third model is actually closer to Facebook's fabric aggregator kind of model, right? In that model, they basically build a chassis with all the one IO box, right? So I think that we are looking at all three scenarios, and we haven't finalized on what is. Maybe all three approach makes sense, but we haven't really kind of finalized on that yet.
Okay, thank you.
Hi, can you talk a little bit more about one, I guess you called it the Open Network Emulator.
That's right.
How do you plan to work with the device, the hardware vendors, each of them, to actually provide the functionality in a virtual fashion?
Yeah. So there's some details still in the works, but the essence of this is that the OS image needs to show up as a VM or container that's available in Azure, right? As long as we have that, and the data plane, we can emulate that, right? So does that answer your question?
Well, I'm thinking a little bit more about specifically on the hardware features and functionalities, right? As devices evolved, think about telemetry, for example, that the hardware is providing some kind of pipelines. And so your emulator is as good as the set of features that is actually available in general. Yeah.
I think that the key thing there is whether the hardware feature is actually describable to SI, right? If it's a control feature, let's say you're adding MPLS. If MPLS description is available in SI, then we can use a SI layer abstraction to emulate that. But with a caveat, one caveat is that very hardware-dependent feature is very difficult to emulate. For example, PFC, right? You cannot use one to emulate the PFC behavior, right? Because the PFC is very hardware-dependent, right? So I think it's probably more easier for you to think of using one for control plane emulation, right? All your routing dynamics, all your control plane dynamics is very super accurate, and your data plane, the speed is not going to be fully replicable. And if you are expecting a very fast pushback of the PFC kind of mechanism, that's difficult to emulate. We are still kind of looking for ways to do that. But, yeah.
Okay, thank you.
Hi. So I saw somewhere on the internet that there are announcements about other network operating systems. I believe from AT&T. And I believe I wonder what's your perspective? Why would AT&T not join the SONiC project and contribute with their effort to you, and instead they sort of decide to start from the scratch and develop their own approach?
Okay, I certainly hope that we can work together on this, right? I think we're certainly open to work together, right? That being said, right, I think that the beauty of open source, right, is that it's choices, right? You do not have to kind of pick one, right? So I think even in Linux community, there's a lot of choices, right? So I think that's one thing that's a beauty of open source community, that everybody makes their contribution and it's available to everybody to look at, right? And you can make choices. Right? I think that's the beauty of open source for one. The other thing is that maybe the beginning of the emphasis is a little bit different, right? Maybe they're emphasizing very much on the telecom scenario, while we were very much emphasized on the data center scenario, right? So maybe the initial of the emphasis is quite different, right? So I think that would be my guess. We do talk to each other and do look for opportunities to work together with each other, right? But I think those things got to happen naturally instead of somewhat being forced. There's nothing that people want to force it, right? It got to be natural, I think. Right.
Okay, thank you. And that brings me to the second question. I wonder, because SONiC's focus is more or less the cloud, and I wonder which kind of features you would accept to the project and which definitely not. For example, let's say STP or other routing protocol. Is it something you as a SONiC project see as important input, or you would rather say, no, we prefer to limit our...
So the way that we think about it, right, is that the application level, that's a reason that we make everything into very containerized, right? So that, let's say if you develop another BGP daemon, right, probably that SONiC already have one BGP daemon, right? But maybe you can write another BGP daemon that works better for your scenario, right? And you are free to swap it, right? So we do not need to kind of force agreement across the whole community. Right, because let's see, for example, right now, LinkedIn, that's our sister team, right? They're running FR, right? And we are still stuck with Quagga. Do I think FR is better? Yes, I think FR is better. I'm not ready to jump into that water yet, right? We had an agreement that our sister team is going to jump into that water first, test out the temperature, we're going to follow into that, right? So it's on our roadmap, but we're running two different things, right? So it's okay, right? If you're adding an FTP container or you're adding an MPLS container into the system, there's nothing wrong with it, right? So I think that we build the infrastructure to be ready for different kind of applications, right? So that's one thought. The other thought is that does it require a fundamental change to the syncd, right? I'm hoping that the current syncd design doesn't force a fundamental change. Let's say if adding spanning tree, I don't see why we need to modify syncd a lot, right? If you're adding MPLS, I don't see it happening either, right? If it's a new system that you're introducing that is forcing, let's say, the syncd needs to be fundamentally modified end-to-end, that would be a little bit tougher for us to kind of absorb in, right? So I think that's what kind of level of change that we're bringing into the system, right? But fundamentally, I do not think that application level protocols are going to be difficult to absorb, right? I think we're pretty open on all those kind of things.
Okay, thank you.
Yeah.
So I'll just add for on to top of that is that while Microsoft is leading the efforts for SONiC and SI, there are lots of other companies that are also contributing. You saw the logos up there, and some of them are large operators also, like Alibaba and Tencent, and they are contributing their own, like if they see something that they need that's not in SONiC, then they contribute that. So there are other contributions besides what Microsoft needs.
Yeah, I think exactly to Scott's point, right? I think the reality of a lot of stuff is that it's going to be operational scenario driven, right? And so we release a default image with all the containers, right? And maybe what's going to happen to you is that you're like coming in and just like LinkedIn, you see, wow, why is this a Quagga container? I want a FR container. Delete this container, put in that container, right? And so that's a pretty natural way of thinking how do you use SONiC. The base layer is the same, and for stuff that you didn't have a strong opinion on, you can leverage the community to get something solid. Right? For stuff that you have a a very solid, strong opinion on, and you want to modify it and get your benefits and make your scenario work, right? That's the community is happy to see that. Right.
Other questions?
Okay.
I have one.
Okay, go ahead. Let's go. Yeah.
So I want to go back to Psi.
Yeah.
And you showed the examples of the flow of the like when
The
you're
data
doing
pipeline.
BGP.
Yeah.
No.
Oh,
this is when
the
you're
BGP.
like you
Yeah.
get your BGP route update and how it goes through the whole SONiC and down through Psi and back in to the ASIC. So what about not events that happen on the net? Well, not packets that happen on the network, but things like MAC learning. These the ASIC learns about and then has to inform. There's a different path, right? Or how does that work?
Yeah. So MAC learning, interesting you brought this up because MAC learning happens on different hardware in a somewhat different way, right? There's a switch in ASIC hardware that takes care of MAC learning almost completely by itself, right? And there's a switching hardware that more or less doesn't do any MAC learning, so the software has to come in every single time, right? So that part is a little bit kind of different because of the hardware nature of it, and because of that, right? So we have to go through the integrate with the Linux kernel, because in kernel we didn't modify any kernel, right? But the kernel will actually participate in MAC learning in certain situation, and in certain situation is purely an API call to the Psi layer, right? So to fetch the MAC.
So that's using NetDev or NetLink. I mean, sorry, NetLink.
NetLink for messaging, right?
Messaging.
But the device driver is NetDev.
Okay.
Right. So basically, I think here's in general, our principle is that we try to stick to the Linux kernel as much as possible, right? And everything else, the short of the side that goes through, because all the SDK is integrated to the user space. So the Psi sits at the user space, but everything else, if the kernel provides it, we leverage the kernel.
Thank you.
Anything else?
All right. Thank you very
good.
much.
Thank you.